I'm Professor Angela Rasmussen from the Department of Electrical and Computer Engineering at the University of Utah. Today we're going to go through an example for DC analysis when you're in the saturation mode. And I want to remind you that handouts for this problem and the other problems I'll go through are located on that handouts and lectures. For this week, it's week 7. All right, so this is going to be the first example that we go over. So here we have a problem where you're told to try to analyze it with it acting in the saturation mode. And so you're going to solve for IBIC and beta forced. And remember, beta forced is the example where you have IC saturated over IB saturated. So this is consuming saturation conditions. You're going to get this ratio, and that is what you're going to have for beta forced. So to do that, we're going to assume saturation conditions, which means that you now are going to say that the voltage drop between that collector and emitter is going to be given by the value VCE sat, and again, this is from a data sheet. So you would get this information from data sheet. So for this condition, you're going to set that voltage at 0.2 volts. And now you can take a loop from your collector to your emitter because you know that 0.2 volts. And you can also take the loop from the base to the emitter because we're going to also know that that diode is on, so that's 0.7 volts there. So the condition between active and saturation is when you have the equal condition between your base and your collector. So condition again is when VC is greater than VB, you're in active mode. When VC is less than VB, you're in saturation mode. And then those relationships do not hold anymore for the saturation region. Remember, that relationship is only for the active region where you can relate IBIC and IE, and that means that IC is equal to beta IB is equal to alpha IE. Only the active region condition can you use that. Otherwise, we can only use the 0.2 volts between VC and E for saturation conditions. So we're going to take a loop still through the same method, loop from base to emitter. So doing that, you're going to go around in this loop. Here you'll have a plus to minus. And if I'm doing the second signs here, this would be a -5 minus, this is IB times 10K, plus minus 0.7, and then this will be a plus for the 5 down there. So that loop again is a -5 minus IB times 10K plus 1 minus 0.7 plus 5 equals 0. And now I can solve this for IB. And the 5 and the -5 will cancel, and I can take the IB over to the other side to get positive, which leaves me with a 0.3 on this side and over 10K to give me 3 times 10 to the 5th, or -5 amps. So now I have IB. Again, I cannot use the relationship like we did with the active region where you were able to relate each one. So from here, I'm going to need to use another loop to get IC. So this is for saturation. So I'm going to take a loop from the top and I'm going to go down. So this would be a plus, this would be a minus, minus, and then I can have a plus there. So that loop, I get a plus 2.5 minus IC, forgot to write that, that's IC, times 20K minus 0.2 plus 5 equals 0. And now I can solve this for IC. So I get 7.5 minus 0.2 for 7.3 over 20K and that gives me a value of 365 microamps. So now I can use those two values to find beta forced. So beta forced is again that IC, and this is for only the saturation. So IC saturation over IB saturation, so 3 times 10 to the minus 5th, all over 365 micro, which is 10 to the minus 6, and I get 12.2. So this ratio, if our beta is typically around 100, we can see that beta force needs to be a lot less than that 100 in order for it to be in the saturation region. So this definitely proves that this value is a lot less than 100, and so yes, you are in the saturation region. So the other question on this one is to say, well, say I designed this and I actually wanted it to be in the active, but it ends up being in the saturation region. What could I change? And most likely it's going to be RC. If I wanted to change RC, because that's something I usually have control over, what value of RC would then move this into the active region? So we want to look at that condition for RC. So we know that the condition, in order for it to be in the active region, we need VC to be greater than VB. And so we can set these values. So VC is going to be the voltage at this node. So we have a plus 2.5 minus IC RC, and this would be in the active region now, would be equal to VC there. So VC is equal to, I'm going to change this to white. So VC is equal to that 2.5 minus IC, now we're looking at the active value, times RC, and this is the value we want to find. So our same, to look at now the active conditions, we're going to take that same loop from base to emitter, so we're going to get that same value for IB. So IB active is actually going to be the same value, which we found was 3 times 10 to the minus 5th. And now IC active is going to be beta IB. And so we are going to use the beta of 100. So it's going to be 100 times 3 times 10 to the minus 5th. And that gives me 3 milliamps. So now from here, I can plug that in for this IC sat active, and we can solve for RC. VB is going to be the voltage, and we know VE is already set at minus 5, and so VB will be minus 5 plus 0.7 to give me a value of, here is minus 5 plus 0.7 for a value of minus 4.3. So I can use VB as minus 4.3. And so this is going to be a minus 4.3. And then I'm going to set that equal to each other. So 2.5 minus 3 milli times RC is our unknown, needs to be greater than a minus 4.3. So I can solve this. I can bring the minus 3 milli over to this side, and that will be less than, and then take the minus 4.3 over to the other side, so it'll be 2.5 plus 4.3. And now I can divide by the 3 milli, and that will give me that my RC needs to be less than this value, which ends up being 2,267 ohms. So as long as my RC is less than that value, it will stay in the active region. So that concludes this example. Thanks for watching.